Okay, in my last lecture, I gave you a nice qualitative description of what is meant by gravitational potential energy. If you take an object and lift it like so through a vertical displacement, the work done by gravity is negative mgh. Therefore, the minimum amount of energy that you need to use to overcome the force of gravity, what is called the work done against gravity, is positive mgh, and that then becomes the potential energy of the object. And then that potential energy is transformed into kinetic energy as the object falls. The amount of kinetic energy that the object has when it returns to its original height is exactly equal to the work that was done against gravity in the first place. Okay, now how do we show all of this mathematically? Specifically, what is special about the force of gravity that gives us this new form of energy? Well, in order to understand that, we have to perform a very specific type of calculation. We have to calculate the work done by gravity over what is referred to as a closed path. A closed path is starting and stopping in the same location. Now I'm going to begin to give us a general description of this on the board, but I'm also going to show you a simple demonstration in just a few moments that will give us some context. But for now, let me copy down the following. Okay, so let's kind of phrase it like this. What is so special about gravity? We're going to set up a very specific type of calculation. We're going to calculate the work done by gravity over a closed path. So a closed path is mathematical lingo for starting and stopping in the same location. Okay, here's how I'm going to diagram this out. Let's say that we start the object here at position A, and then we move it like so to here, position B. When we move it from A to B over some path, we undergo a height change. Let's consider this at point A to be height 0, and then therefore here at point B, let's consider this like so to be a height h. And then what we'll do is we'll move back, downhill if you will, from point B to point A, like so, thereby completing what is called a closed path. We start and stop in the same location. Now, just to give us some context here, I'll tilt the camera in just a moment, we're going to envision the closed path as the path that is traced out by a pendulum. So for example, okay, let me reposition my camera here. So bear with me a moment as I do. Like so. Okay, and then I have a pendulum like so, and then let's consider this right here to be point A. Point B we'll say is somewhere over on the other side of the swing, but then ultimately we return to point A again when I do this, like so. We're going to calculate the work done by gravity over this closed path. Okay, before I move back to the board to begin this calculation, a couple of things here about the pendulum itself. We're going to ignore a little bit of friction here that occurs between the rope and the attachment. We're going to ignore air resistance. Therefore, the only force that matters here is the force of gravity. Now, in addition to the force of gravity, of course, there is also the tension from the string. But the tension from the string is always perpendicular at any instant in time to the displacement vector of the pendulum. So as the pendulum completes a circular arc like so, think of this right here as the radius of that circle, which is then therefore perpendicular to the displacement at any moment in time. So what this means is that the tension vector does no work for this reason. So if the tension vector does no work and there's no friction and we ignore air resistance, then the only force that matters here is the force of gravity like so when I complete this closed path. That will become a little bit more important later on as we get deeper into this lecture. Okay, let me re-tilt the camera back. Okay, so let me move this back. Like so. Okay, and now we get to the calculation itself. How are we going to calculate the work done by gravity as we go from point A to point B and then backwards from point B to point A? Well, because I'm tracing out here an arbitrary closed, or rather an arbitrary curved path of some sort, what I'm going to have to do is set up a line integral. So So ultimately, the work done by a force over a curved path is described by the following expression. But describing this expression here for gravity is easy to do. Okay, first of all, the force vector. The force vector, of course, is straight downwards. That's the force of gravity. So let's immediately write the force vector F as minus mg j hat. So this is in the negative vertical direction, hence the negative j hat notation. Okay, and then we have the infinitesimally small path, dr. So imagine, for example, that right here, like so, is an infinitesimally small path dr. And now off to the side, let me go ahead and draw this. And what we'll do is we'll break it into components. Here's a horizontal component we'll call dx. And then right here is a vertical component we'll write as dy. So then therefore, in component form, this infinitesimally small displacement vector dr is dx I hat plus dy j hat, like so. Okay, and now let's just put everything into the dot product here to calculate the work done. Okay, so in general, the work done is going to be the following integral. So here's the force of gravity straight downwards, and then we multiply that here by the infinitesimally small displacement vector. That is like so. Now recall the shortcut associated with calculating a dot product between two vectors that are in component form. You multiply, for example, the x components together, you multiply the y components together, and then you add everything up. Now, because the force of gravity only acts vertically downwards, no work is done by gravity whenever the object is moved horizontally. In other words, there's no I hat component here to gravity. Think of it as 0 I hat, if you will. So then 0 multiplied by dx here means that no work is done horizontally. So think of it in general like this. If you take an object and you step it horizontally like so, your displacement vector dx is always perpendicular to the force of gravity. So no work is done by gravity whenever the object is moved horizontally. The only thing that does matter is taking the object and moving it vertically. This is why earlier when I said the following, that is, if you take an object and lift it vertically, and then secondly, if you take the object and move it over some strange path like so, in both cases, the work done by gravity will be exactly the same. We'll see that here in the calculation in just a few moments. Okay, so now if I simplify this expression, the work done by gravity in general then therefore becomes the following, like so. So I did my dot product here, the dot product between this vector and this vector, that then gives me this. The only thing that does matter is taking the object and stepping it in the vertical direction. So now let's go ahead and set up the integral as we go from a to b and then backwards from b to a. The only thing that will change as we do these two steps here are the limits of integration. They'll just reverse. So for example, let's now go from a to b. So as we go from a to b, the work done by gravity, and let me go ahead and write that phrase out here for clarity. The work done by gravity is going to be the following integral, negative mg dy, and now we're integrating in the vertical direction from height 0 at position A to height h at position B. Now the negative mg here is a constant, so let's just go ahead and pull it out of the integral like so. And then the integrand here is just the number 1, which is not written down. So if we're integrating in terms of the variable y, and the integrand here is 1, the antiderivative then therefore gives us the following expression. And now we evaluate this between 0 and h. So take the h and plug it into the function first, and you just get negative mgh, and then minus 0 when 0 is plugged into the function. So then therefore, when you take an object and you lift it vertically in some manner, as we've already described, the work done by gravity is negative mgh. It doesn't matter if you move it directly like so, or you move it over some strange path like so. That's what this calculation shows. Okay, now we just go backwards to complete the closed path. Now we go from B to A. Basically, we're just going downhill. So then therefore, as we go from B to A, all that happens is that the limits of integration reverse. So now we go from B to A. So the work done by gravity is that, once again, the exact same integral as before. That is this expression here, but now we go from h to 0. When you reverse the limits of integration, The only thing that happens mathematically as opposed to the earlier calculation is that instead of getting a negative MGH, you end up with a positive MGH like so. Okay, now we add the two terms together to complete the calculation, the work done over the closed path. So add to obtain the work done over the closed path. And notice that the total is equal to 0. To write that down. It's crucial that you do. And now here's the heart of this lecture. What does this mean? Pay very close attention. What I'm going to do is once again use the pendulum here to illustrate. Let me re-tilt the camera. Okay, so let me tilt the camera once again so we can observe the pendulum. There we go. And now let's go ahead and take a look at, yes, it's an oscillation. I'm going to take the pendulum and position it here and then release it, and then it returns to here. And then as we just calculated, the work done by gravity over this closed path is 0. Remember that the tension doesn't matter, we're ignoring friction, and we're ignoring air resistance. The only thing that matters here is gravity. So then therefore, as the oscillation occurs from here to here, the work done by gravity is 0. This then means that gravity is neither adding energy to the object or removing energy from the object. However, you can see with your own eyes that the kinetic energy of the pendulum is changing as the oscillation occurs. But if the kinetic energy is changing and gravity is not adding energy to or removing energy from the object, then the kinetic energy has to be transforming back and forth into something else. And that's obviously potential energy. This then literally proves that potential energy exists. Forces that have this mathematical property, where the work done by those forces over the closed path is equal to 0, are referred to as conservative forces. There is always potential energy associated with conservative forces. Gravity is one example of a conservative force. A little bit later on, we'll see that the spring force is also an example of a conservative force. The force of electromagnetism is conservative, the nuclear forces are conservative, and so on. So forces that have this mathematical property, where the work done by that force over the closed path is equal to 0, then therefore potential energy exists associated with those forces. Okay, let me re-tilt the camera back and then briefly write that on the board. Like so. Bear with me here as I do. Okay. Okay, so I'm going to do some erasing here. Okay, now let's specifically use the pendulum to conceptualize this situation. Use a pendulum to visualize. So as the pendulum oscillates over a closed path, gravity does not add energy to or remove energy from the pendulum. That's what the calculation means that we just performed. The work done by gravity over the closed path is 0. Therefore, as the kinetic energy of the pendulum changes, as it oscillates, it has to be changing into something else. In other words, another form of energy must be present, and that's potential energy. So as the pendulum oscillates, its kinetic energy must be transforming back and forth into potential energy. What we have done here is we have now proved that potential energy exists. This calculation proves that potential energy exists. Once again, forces that have this mathematical property, the work done by those forces over a closed path is equal to 0. They are referred to as conservative forces. Gravity is an example of a conservative force. Okay, so what I'm going to do here is I'm going to pause the video here before we now get to the punchline. The punchline is then using what we've done here to illustrate then what is referred to as conservation of energy. Everybody, of course, in class from prior science classes is familiar with the idea of conservation of energy. Energy is neither created nor destroyed, it is only transformed, for example, from one form to another. We'll use the pendulum to illustrate that, and we'll use it along with a portion of the calculation that we just performed.